So I am recording now, just for those of you who need to know that. Oh dear, the video keeps going off. Let's try again. There we are. Oh, that's not good. Something's going wrong there. Right, okay. Just for those of you who are conscious of recording, and I will post this up on Show My Homework in the slot where I put this particular lesson, so that you can watch the playback afterwards. And just one more person joining. I'm going to ask them to identify themselves. Hi, one of you is identified as Zoom user. Could you just tell me who you are, please?
Yeah.
Okay, thank you very much. Thank you for informing me, and welcome to the class. Yeah. I hope you're going through the Seneca task that I've given you.
Yes, I have.
Yeah, I noticed you've done about the first three sort of the first 3 units on it. Yeah, keep playing through that. That will help you to catch up. When you feel ready to, then you can start having a go at the practice papers. But this lesson I think will be useful for you, because you'll see what kind of things you have to learn how to do. So if we go through this exam paper, this is another practice paper. These are made up from what I call reject questions. They're questions that I sort of designed for the UFP Physics Unit 2 exams, but maybe didn't use because of just little issues with them. So it's not a perfect paper, but it gives you really good practice. So as ever, we start with question 1. A good big piece of exam technique, by the way, is to make sure you've read through the whole paper before you start it. There are a couple of different reasons for it. One of the big ones being that what you do, that when you read through the paper, is your brain starts sort of processing questions in the background, and it helps you to answer them. But it also just helps you to become familiar with what's in the paper. Right, so this one is a student devising an experiment to measure the time a projectile spent in the air and the maximum height reached by the projectile. She takes the same measurement 3 times. So they fired a projectile into the air, and they've got 3 different values for the maximum height and 3 different values for the time taken. So it's a little bit different to some of the previous questions that I've set you. So the first question says, suggest the apparatus used to measure the values below, and also suggest the uncertainties or sensitivity of the equipment used. So the time, well, they measured it with a stopwatch. There's quite a large uncertainty in the value. You can see straight away there's a bit of a spread here. So they probably likely used a stopwatch. Okay. And for the distance, well, they measured to the nearest centimetre. So they probably used something like a ruler or a centimetre scale. Okay, now sensitivity, most of you got this, so I'm not going to spend a long time on it. The sensitivity, to find the sensitivity of the apparatus, it's implied in the measurement here. So here for the time taken, it's the nearest 100th of a second. And for the ruler, it's the nearest 100th of a metre or nearest centimetre. So that's the first question answered. The way it's marked is it's half a mark for each bit and then rounding down. So if you got one of the sensitivities wrong, then you only got 1 mark. But most of you got that one right. It then asks you to calculate the mean value of the time taken and the height reached and enter it into the table. Now, I've got my scientific calculator here just to point out a common mistake that people make. I'm going to show you the wrong way to do it first, and then I'll show you the right way. So if I was going to get the average, the mean value for the maximum height, it was 0.55 plus 0.52 plus 0.50 divided by 3 actually gives you something that's completely the wrong answer. You can tell straight away that it's completely the wrong answer, because the value here, 1.23, is completely different to these values here. It should be somewhere in between the maximum and minimum value. So that's been done incorrectly. So what it should be is 0.55 plus 0.52 plus 0.50 You then press equals to get the answer and then divide it by 3. So 0.52, and we should use appropriate number of significant figures. So everything here is to 2 significant figures. You can get away with 3, but really I should call it 0.52, 2 significant figures all the way. The next one is the time taken. Exactly the same, do exactly the same method. I'm not going to do it in front of you because most of you did that reasonably well. It came out to be 0.65 seconds. So that's your calculation. The next part is calculating the uncertainty in the measurement. So there's a difference between the uncertainty or sensitivity of the apparatus. So for example, the stopwatch is sensitive to the nearest 100th of a second, but here we want to measure the uncertainty in their measurement. We're looking at the measurements. So it's maximum minus the minimum. So the maximum value is 0.7 and the minimum is 0.6. So it's 0.7 minus 0.6 divided by 2. It's the range, the difference between the maximum and minimum value there for the same measurement, divided by 2 gives you 0.05. And is that the final answer? No, because it wants the percentage uncertainty. So it wants it as a percentage. So for the time taken, I've then got to take that value and divide it by the mean value. Mean value is the one I calculated here. You can use extra significant figures if you've got them written down somewhere. I'm just going to use 0.65. And what that's given me is 0.077. So that would be, for the time taken, about 7.7%. So you can write it at 7.7%. You could round it off to the nearest whole percent if you wish to. The next thing to do is to calculate, do the same for the height reached. So again, it's the range over 2. So it goes from 0.55 to 0.50. Divided by 2 gives you 0.025. And you then divide that number by the average value, which is 0.52. That was the average, or the mean. And that gives you 0.048. So again, that would be 4.8%. I would accept 5%. Oops, sorry, I've gone off the bottom there. I would accept 5% on that value. Now, the next question, it asks you, you're given a formula, and the student uses the formula below to calculate the acceleration of a projectile. So you're given a formula, so you know what's coming next. There's a calculation which just gives you the opportunity to display your ability to get the correct units. The calculation itself is pretty trivial, but we always write down the substitution. So 8 times 8, that's the average height, which we calculated to be 0.52. Divide it by t squared, 0.65 squared, and that gives you the correct units. That gives you 9.85. But unless you quoted the unit correctly, meters per second squared, you didn't get the mark. So it's 1 mark, and really the mark is for that bit. So, well, but it didn't award it if you calculated it incorrectly, because, well, I don't think anybody actually would. So then you have to calculate the percentage uncertainty in the pupil's measured value of the acceleration of the ball. Now, remember, you can do this by range, or you can do it by direct calculation. I prefer direct calculation. I find it easier. So what I'm going to do, I'm going to start with my formula. Well, I know if I've got divided by t squared. I'm sorry, Pascal, you seem to have logged in twice. I'm going to mute you. feedback on your speaker. There we go. So we've got h divided by t squared. So when you're dividing or multiplying, you're adding together percentage uncertainties. And here we've got to add them to get added twice because you've got t multiplied by t, or t squared. So we're looking for the percentage uncertainty. And again, that's all it wants. It doesn't want the absolute uncertainty. So the percentage uncertainty in the measurement of the acceleration, that would be the percentage uncertainty in the height plus, because it's t squared, it's 2 times the percentage uncertainty in t. So that then gives you, well, we've actually calculated these. So the percentage uncertainty in the height is 0.048 plus 2 times 0.077. So these are calculated before, and if you miscalculated the percentage uncertainties in the earlier part of the question, then the error does carry forward as long as I can see that's in the working, because I've got to be certain that that's the only reason why you got the answer wrong. So if I calculate that, that comes out to be 0.202, which is 20.2%. Well, I would have to say 20%. Is my answer. Okay, it's 3 marks. 1 mark for recognizing how to for using an appropriate method, 1 mark for doing a correct calculation, and then 1 mark for converting it to a percentage. So quite easy marks in there. It then says suggest a reason for high uncertainty in this experiment, and also a way that the experiment could be adapted to reduce the uncertainty. So there are 2 sources of uncertainty here, and here it could be to do with timing. Okay, because the timing, because it was manual. Okay, but it's also the maximum height reached, because it's a ball being sort of thrown upwards. So it's very hard to gauge exactly how high the ball went. So it's only at the top for a short time. Okay, that either one of those would have done nicely to get 1 mark, but then you've got to look at the actual adaptation to the uncertainty. It's not really going to work to use light gates and in this particular situation, simply because the ball's being thrown upwards, it's going back down again. It's not likely to pass through the light gates very easily. If you remember when we were doing G by free fall using light gates, we discovered that actually the ball often missed the light gate. So it's not the best way to do it. So probably the best way to do it is to use a thing called a motion sensor. And actually what they do is they use ultrasound. So it's ultrasonic. Oops, just trying to spell that correctly. What happens with an ultrasonic motion sensor is you have your motion sensor there, connected to a data logger. And you have your ball being fired upwards. As the ball's being fired upwards, the motion sensor sends out pulses of ultrasound which go down, then they reflect off the ball and come back to the sensor, so it can measure the distance. That way you can actually get a recording of the distance the ball is away from the motion sensor at any given time. So you end up with a nice graph on a screen that you can read much more easily. So that is the best solution for that. Light gates weren't really going to do it on this occasion. Right, on to question number 2. Now, question number 2, I tried to be as inventive as I possibly can. So we've got somebody who can run very fast. I'm sure most of you recognise this particular athlete. So table 2 contains some data about the person, and it tells you should assume that the runner accelerates at a constant rate throughout the 100 meters. So we started to get key data here. So we're looking at a constant acceleration question. Question 2 is always about constant acceleration or constant speed, and there's usually a little bit of energy and motion thrown in there as well. So you have to show the average acceleration of the runner is approximately 2.2 meters per second squared. Now, some of you had a go at this, but then kind of, I'm not too sure, but it just seemed to get a little bit sort of mixed up. So we're using a Suvat equation, okay? Obviously the mass here is going to be irrelevant because we don't have the force. If you had the force which is pushing, then you could work out the acceleration using Newton's second law of motion. But in this case, we don't have that. So we've got to look at what we do have. Well, we've got the time, we've got the distance, 100 meters. Okay, so it's a Suvat equation. Because we've got the distance, we don't know their final velocity yet. We want to work out their acceleration. We've got the time, but what else have we got? Well, we've also got their initial speed, because if they're a sprinter, their initial speed is going to be 0 because they start off in the starting blocks. The gun goes off, the stopwatch starts, and they run. So initially, their initial speed is going to be, or velocity is going to be 0. So to show that the average acceleration is 2.2, we've got to use a Suvat equation. The one that's most useful, I think, there is to use S equals UT plus a half AT squared. Okay, and we want A. So A is equal to S minus UT, just going to rearrange it, divided by a half, what's the same as multiplying it by 2, and dividing it by T squared. So if that's the case, well, the UT is going to be 0. So really it's the distance, 100, that UT, because the initial speed is 0, then U times T is 0, because anything multiplied by 0 is just 0, divided by T squared. So it's multiplied by 2, because this factor of 2 is in there. Some of you, when you're working on this, you forgot about the factor of 2. You worked it out to be 1.1, and then seemingly arbitrarily multiplied it by 2. And I couldn't really tell what you were doing, so I couldn't give you the mark. And the time squared, well, that's 9.58 squared. And that comes out to be 2.18 meters per second squared. Now, when you're asked to say that something's approximately, what you should do is go to one extra significant figure to show that it rounds off to that number, or comes very close to it. The next thing is to calculate the force needed to achieve this acceleration. So this is the runner's accelerating force. That's going to be F equals ma, because we now know the acceleration. Even if you couldn't calculate it, you're given this number here. So the mass is 80 kilograms multiplied by acceleration of 2.2, or you could use 2.18 if you wish. And I make it 174 newtons. It could be 176 if you use 2.2. Again, I'm not so concerned about this number. I'm concerned about this bit here, using the physics. Remember, you're being examined on your use of physics, not your ability to just come up with correct numbers. Oh, there goes my camera again. I need to change my camera over. So if I calculate the speed of the runner at the finish line, well, again, I've got to think about what formula I'm going to use. You can use quite a few of the Suvat equations now, but what I'm going to do is I'm going to use the idea that the distance traveled is going to be the average speed multiplied by time. Why? Because that gives I can use lots of my original values here, but you can use any valid Suvat equation. So to get the speed of the runner, we can rearrange that. We know that U is 0. So it's 2S over T, which is going to be 2 times 100. So that's 200 divided by 9.58, which gives you 20.9 meters per second, or 21 meters per second. Okay. You can give this to 2 or 3 significant figures, as we've got 3 here, and we're not certain as to how many significant figures we really have here.
Excuse me, sir.
Yeah. Yes.
In the last bit, can I use distance over time to get the answer? Right.
The trouble is you could use distance over time if he wasn't accelerating. At the beginning of the question, it tells you he's accelerating at a constant rate. So he's actually accelerating constantly over the 9.58 seconds and 100 seconds. So you have to use his average speed, which if it's constant acceleration is v plus u over 2. Okay, does that make sense?
All right.
Thank you very much
Yes.
for asking that question.
Yes,
That's a good
yes.
question. So the next thing to do is to calculate how far the runner travels after just 5 seconds. So here we've got to be a little bit careful. Here we probably want to use our value for acceleration, because if we use s equals ut plus a half at squared, that is our Suvat equation. You do have to remember a lot of your Suvat equations. We know that u is 0 because he starts off from rest. So really it's a half at squared. So it's a half times, again, you can use 2.2. I use 2.18 because it gives me a more precise value. And t squared, well, it says here it's 5 seconds. And this is the bit that people miss. So it's just 5 seconds. So it's 5 squared. So if I calculate that, that comes out to be 27.25, which I should round off really. Well, I can round it off to 2 or 3 significant figures. So it'd be 27.3 meters. Okay. The common misconception that people made was that they thought he was running for 5 seconds after he'd reached his top speed at the end. So now it says describe and explain.
Sorry.
Yes.
For I, why can't you use S as equals to U plus V over 2 times T?
Sorry, S equals what, sorry?
Average speed times time. Because
you don't know what his speed is after 5 seconds. You could calculate it, but it's going to a level of complication that you don't really need.
All right.
Okay, because you're not using his speed at the end of the race, because it's different to the speed he'll be doing after just the first 5 seconds.
All right.
Misconceptions people make. That's one of the misconceptions that people make. Thank you for asking about that. The other one is to just use their speed. Is to just use speed as distance over time, which is if it's constant speed, and it's not, it's accelerating. So describe and explain how the acceleration of the runner would be different if they ran 200 meters instead of 100 meters. Well, we know it's very, very similar to a terminal velocity question. We know the acceleration would decrease. And this is due to, well, it's increased resistance forces or increased drag. Okay. So it says here on the next part, so sorry, this is one mark to describe and explain. So describe is to say what would happen. So we know the acceleration would decrease. Explain is to say why. So it's 1 mark for the description, 1 mark for the explanation. The runner reaches a top speed after 100 meters. It says explain in terms of forces why the runner reaches a constant speed but still needs to apply a force. Well, it's exactly the same as before, but it's just slightly different because now it's at constant speed. So it's the idea that the force is equal and opposite to resistance forces. Okay. And well, it's 2 marks. So I want a second part. I want a qualifier really, because that's fine. But you then need to say that then there's no net or resultant force. I use net because it's easier to spell, which implies no acceleration. Okay. So 1 mark for the idea that we still said that it's equal, that the forces then become equal or balanced. Then the idea that means there's no net or resultant force on the runner, which means they don't accelerate. Now, this question, a lot of you used what I'd shown you before to prove that power was equal to force times speed. However, that's not what the question asked. The question asked, show how it's dimensionally correct or homogeneous. What that means is that you want to look at the units. So the power is in watts, okay? And remember, watts is power is going to be energy over time. So that's going to be joule, so energy over time. So that's joules per second. The joule is a force times a distance. So that's newtons, meters, seconds to the -1. A newton is a kilogram meter per second squared. So it's kilograms meters per second squared times meters seconds to the -1. So that would be kilograms. You got meters times meters, so meters squared. And then seconds to the -2 times seconds to the -1, so that's seconds to the -3. Now remember with the force, that's power, sorry. The force is therefore going to be newtons, which is kilograms meters per second squared. And we know that speed is meters per second. So if we combine the two, you've got kilograms, meters times meters, seconds to the -1 times seconds to the -2, seconds to the -3. So you're showing that the two are the same. Okay, so that's how you do that question. It's what we call a all equations that are valid are usually homogeneous. Excuse me. Next one, the next part is to hence show that the runner produced approximately 3.7 kilowatts if they push with the same force calculated in A part 2. It's not quite right, it's not quite realistic, but it'll do. So if we look at A part 2, we're looking at the formula first of all, because there's hence, in other words, using that. So the force is 174 newtons or 176, depends upon which value used to calculate it, multiplied by the speed. Well, if he's traveling at top speed after the 200 meters, which is not very realistic, but we'll pretend 20.9 meters per second is what we calculated before. You end up with 3,636.6 or something like that watts, which is 3,700 watts, which is 3.7 kilowatts. Now for 1 mark, the bit I was looking for was the calculation of this value here. If you didn't get that one right, I then looked back to see if I could find your working and see if it was an error carrying forward. But your clue as to whether or not you got the previous questions right is the fact that if this value is going to be wildly different to 3,700, then it means that somewhere along the line there's been a mistake. Right. Last but not least, estimate the amount of work which would need to be done to run an extra 100 meters. Now it's estimate. So we're assuming the same force, which is 174, multiplied by the distance traveled, because work is force times distance. So it's an extra 100 meters. There we are. So it's 17,400 joules. Quite an easy question when you think about it, and it's a very easy 2 marks. This was really sort of the.
Gary, could you repeat what you said?
Sorry. Yeah, work done.
Could you repeat what you said?
Is force times the distance. So the distance here is 100 meters. Okay, just to run the extra 100 meters, not to run the whole race. So if he's applied a force of 174 newtons, that's his sort of maximum running force, multiplied by a distance of 100 meters, gives you 17,400. So it's a 2 mark question, a very easy 2 marks. So basically it was 1 for the right answer, 1 for recognizing that it's the force times the distance. Quite an easy 2 marks if you had the confidence to continue. The reason why I put this part in the last part of the question was because it's kind of a resilience test. It helps helps to remind people that often, even though they might struggle with a question, it's worth sort of carrying on with the question, not just giving up after sort of the second bit when you find something that you find difficult to do or that you can't do. if you just use estimated values, as long as that's the answer to, you know, say for instance, you couldn't work out the force, so you just went back to your force question and wrote a sensible-ish number. If you multiplied that sensible-ish number by 100, then you got the 2 marks because the error carries forward. So it's all about sort of reminding you to be resilient when you're answering the questions, because a lot of people sort of give up about halfway through question 2 on this paper. So you're either going to get, for question 3, you either get the graph or the momentum question. They kind of alternate between the papers. So we've got an interesting game. Billiards is a game which involves collision of 2 smooth identical balls on a table. Now here's a big clue. Our first clue: identical. So they're both going to have the same mass. The object of the game is to make the first ball hit a second ball, which then rolls into a hole. You have to state the principle of conservation of momentum. Now, careful, it's 2 marks. So a lot of people said the total momentum before equals the total momentum afterwards, or words to that effect. But, or that the total momentum of the system is constant. However, it's a 2-mark question. So to get a second mark, you have to put the extra bit in if there are no external forces. Okay, to get that second mark. And loads of people missed that mark because they didn't spot that it was a 2-mark question. Therefore, you need a more complete answer. If it was a 1-mark question, you'd get away with that. However, this is 2 marks, so you need to actually add the extra little bit there. So then it says, during the game, a ball is made to collide with a stationary ball. You're given some data. Again, it's using data from the table. You're told the mass of each ball is 150 grams. So that should immediately translate into kilograms. You're told the initial velocity of the first ball before the collision. Initial means at the beginning, so this is before the collision. Final velocity after the collision is 0, so it stops. And the distance to the hole is 1.1 meters. So calculate, first of all, the initial momentum of the first ball, and state your answer to appropriate numbers and figures, and include a correct unit. So here, we need to actually calculate the momentum. Well, momentum is mass times velocity. So momentum is 0.15 multiplied by the velocity of 1.5, which gives you 0.225 kilograms meters per second, because that's the correct unit for momentum. You could get away with Newton seconds, but that's usually to do with impulse or changing momentum. Now, in terms of significant figures, really, these values, well, they're 2 significant figures, really. So that should be 0.23 kilograms meters per second. That should be the correct answer, because everything given here is 2 significant figures. This one's a bit dubious, but the rest are just 2 significant figures. Then it says, state the total momentum of the 2 balls before they collide. Well, the second ball has got no momentum, okay, because it tells you that it collides with a stationary ball. Again, big clue there. So the initial speed of the second ball is 0, so its momentum is going to be 0. So it's exactly the same, 0.23 kilograms meters per second, okay? As long as that answer was the same as that answer, I gave the mark. It then says, hence show the velocity of the second ball after the collision is the same as the initial speed of the first ball. So what you need to do is do a before and after. So before, the first ball has a momentum of 0.23. Well, I'm going to use my more precise value of 225. Whoops, gone off the bottom there. Okay. Plus the initial momentum of the second ball, which is 0, is equal to the momentum of the first ball. Now it tells you the final velocity after the collision is 0. So we know that's the momentum of the first ball goes from 225 to 0, sorry, 0.225 to 0, plus the momentum of the second ball, which is going to be the mass, which is 0.15, because it's identical to the first one, multiplied by V. So then we sort of rearrange it for V. Well, that's 0.225 divided by 0.15. So all I've done is rearrange it and get rid of the zeros because they're just in the way. And that comes out to be 1.5 meters per second square, meters per second. If you use 0.23, then obviously you get a slightly higher value, which you would then compare with the initial speed of 1.5 and say that they're similar. So that's how you answer that question. It's all about being able to really sort of pick out the important parts of a question. It then says, discuss whether or not the collision between the two balls is elastic. In other words, don't just say it is or it isn't. You need to kind of say why it is and possibly come up with some evidence. So it's elastic. I can tell you it's elastic, but how do I know it's elastic? Well, one of the definitions of elastic, one of the examples, sorry, of an elastic collision is billiard balls or pool balls or snooker balls. It's also subatomic particles. But we really want to be a bit more precise than that. Well, it's the idea that kinetic energy is conserved. How do we know that? Well, that's not enough for 2 marks, really. But so how do we know that? Well, it's a half mv squared. So it's a half times a mass of 0.15 times 1.5 squared before, because the other ball has no kinetic energy, is equal to a half times 0.15 multiplied by 1.5 squared, which is afterwards. So if I'm showing that kind of calculation, even if I'm not completing the calculation, if I'm showing that I understand exactly why the kinetic energy is conserved and therefore it's elastic, then I get the 2 marks. I gave the benefit of the doubt quite a bit on this question. So it then says the ball strikes the cushion at the edge of the table at right angles. Ooh, there's a little bit of a typo in there. Let's put a space in, never mind. At right angles to the cushion and rebounds with a velocity of minus 0.9 meters per second. So calculate the change in kinetic energy. So it's the kinetic energy before, a half times 0.15 multiplied by 1.5 squared minus a half multiplied by the same mass, mass hasn't changed, multiplied by the new velocity, which is minus 0.9 squared. Of course, when you square it, the minus sign disappears anyway, and you end up with 0.108 joules. Okay, you could also say 0.11 joules. That's absolutely fine. Either answer was absolutely fine on that one. It then says the collision between the cushion and the ball takes 0.02 seconds. Calculate the change in momentum of the ball. So the change in momentum is the momentum before minus momentum afterwards. So the momentum before, that's pretty trivial. Subtract the momentum afterwards. Now, you've got to be careful here. It's going to be 0.15 multiplied by minus 0.9 because it's going backwards and it tells you that the velocity is minus 0.9. A lot of people miss that bit out. So the change in momentum, if you calculate it, if you work it out, it comes out to be 0.36. Now it's a change in momentum, so the unit you give is Newton seconds. If you gave it as kilograms meters per second, that was absolutely fine. There wasn't a mark for the unit, but that was how you did it. The mistake that people make most commonly is forgetting that that's a negative. So you've got to, so effectively you're adding the two momenta together. It says hence, in other words, using your previous value, calculate the force on the ball on the cushion during the collision. So we know that our adaptation, our original Newton's second law of motion is actually that the force is proportional to the rate of change of momentum. So the force is the change in momentum, delta mv, divided by the time taken. Here we've got the time taken here, 0.02. So we've got our previous value, 0.36 divided by 0.02, which comes out to be 18 newtons. Okay, that's how you do it. 1 mark for recognizing that force's rate of change of momentum or momentum over time, 1 mark for the answer on this occasion. But again, the error carries forward from part one, from part two, as long as I could see it clearly. Right, a bit of a sporty theme to this paper, because in this question, it says you could ignore the effect of air resistance. Okay, lovely. That's what I'd like to know. Figure 2 here shows a high jumper. They run and jump to achieve the highest jump between leaving the ground and landing. The jumper launches themselves at an angle of 70 degrees to horizontal and then lands at Y. On figure 3, draw the approximate trajectory of the high jumper. Now it wants a trajectory, that's the path they take, and it wants it approximately, so you don't have to measure 70 degrees, but it has to look about right. So it would look something like that. What am I looking for? I'm looking for a parabolic shape, okay? And I'm looking for it being roughly symmetrical. Those are the two things to look for there, okay? As long as it looked about right, I gave the mark. If you sort of did one that was down there, I gave you the benefit of the doubt, as long as it was still a parabola. The mistakes that people make, which I'm going to do in red, one of the mistakes that people make is they do that. Obviously, that's wrong. Some people just draw just a tiny bit sloppily. They sort of draw, they draw something like that, which again is not right. They want a parabolic shape and they want it to be roughly symmetrical, because that's what we're after. How do I know I'm just after the shape? 1 mark. So it's something simple. Right. Now this is a bit of a mathsy graph drawing question. So I want to calculate, I've got my angles here, they've got the height reached here, they've taken the measurement twice, and I've got some difficult calculations to do. So here it's sine squared. Now the mistake people made when they're drawing the graph a lot is they forgot to square it after do the sign of a value. So I'm going to show you this one with just the first couple of values, then I'm just going to write them in. So if I want to do the sine squared of 10 degrees, I'd literally, on my calculator, I'd press the sine button and I'd type in 10 degrees, I'll press equals, and then you square it. So 0.030. Now, when you're doing this question, here, we want to try and have 2 significant figures, but you can get away with 3 on this one. So I'm going to use 3. So basically do exactly the same every single time, and you fill in with the correct number of significant figures. Now, if you did this to just 2 decimal places, that would have been fine. That would have been absolutely fine. But here I've used 3 because it's the sine of an angle. Now, the other thing here is there's no unit here. The reason why there's no unit is the sine of an angle is actually a ratio. Okay, I'll come on to that in a minute. If you've got a height h in meters, again, it's the mean value. You can see it's quite a spread here, but basically it's the mean. And we want 2 significant figures here. And where we have 3 significant figures, we want to have 3 significant figures. Basically, you've got 1 mark for correctly calculating that column, 1 mark for correctly calculating that column, and having all your values of 2 or 3 significant figures. Okay. Fairly straightforward, and it is a simple calculation. It's usually between 1 and 3 marks for doing the calculations. It's a very easy couple of marks, so it's well worth doing. Now, the next part is using the graph paper. You have to draw a graph of length, jump length, well, it should be jump height. In fact, I think on your one it was jump height, on the y-axis versus sine squared on the x-axis. So if I look on my version, I'm not going to draw it on there. I'm going to show you my version, because otherwise you're just sitting watching me draw a graph, which I think some people might find interesting, but maybe not. So if I look at my example graph here, now this one isn't an easy one. Oh dear, my camera's on the blink. I have to get a new camera, I think. This isn't an easy one to actually to put a scale on, but I worked out that really when you look at your data table, I'll go back to my data table. When you look at your data table, if I compare my values for the sine squared, my maximum value is as near as makes no difference 1. So, and this is tiny in comparison. This is about 3% of it. So I can put 0. I can put the sine squared can go down to 0. So I'm looking to go from 0 to 1. And my height h, well, again, this is a tiny percentage of that. So again, I could go from 0 to about 3.25 or something, or 3.5. So my height h is from 0 to 3.5. So if I'd just done 1, I've done 1, 2, 3.5, I'd have only used that much of the graph paper. I want to make maximum use of the graph paper. Scale is worth a mark. And the same goes with the sine squared of theta. It's here. Obviously, I couldn't make it 0.1, 0.2, and so on, because that would just go off the end of the graph paper. So I managed to sort of halve it. Remember, we're always looking for simple scales. It needs to be that it uses up approximately half of the graph paper. If you imagine drawing a rectangle where your bottom point and your top point form a rectangle, that rectangle needs to be half or more of your graph paper, really. So that's a mark for your scale. The mark for your units and labels: height in meters, sine squared theta in meters. Now the reason why, sine squared theta with no units. The reason why that is, if we think about it, the sine of an angle theta is the opposite over the hypotenuse of a triangle, okay, which is measured in meters. They're both measured in meters or centimeters. And so the unit cancels out. So the unit of the sine of an angle is just a ratio. So there's no unit there. So you don't put a unit there. If you put degrees, I let you off, but just remember in the future. Now, as I look at your plots, well, actually this one, because it was a computer generated experiment, the plots fell on a line quite nicely. So your line of best fit pretty much goes through all the points. Again, as I say, when I'm marking a paper, I tend to check a couple of points if I possibly can. 1 or 2 of you didn't use graph paper, you just used line paper. So I gave the benefit of the doubt on that particular occasion. Okay, so it's 1 mark for the scale, 1 mark for the labels, 1 mark for the plot, 1 mark for the straight line of best fit. It actually does tell you in the question to draw a straight line of best fit. So if you've got a curve, that will tell you straight away that you've made a mistake. And the mistake that some people make when they're doing this question is they forget to square the sine of the angle. They just put the sine of the angle, which means you get a parabola. So that's that part of the question. Fairly straightforward. The next part is calculating a gradient of the graph and give the appropriate units. Here's where the degrees I had to penalize for, which is why I gave the benefit of the doubt on the graph, because I didn't want to double penalize you. So when you calculate your gradient, remember it's delta y, the change in y over the change in x. You pick 2 convenient points. What do I mean by convenient? They're easy to measure, okay? It just makes your life easier. So here, this y1 is 3.5. Well, every 2 squares is going to be 0.1, so that's 3.6. Here it's 0.1, 2, 3, 4. The x is here at 1.1. How do I know it's 1.1? Well, every square is 0.2. That's exactly halfway along, so that's 0.1. So it's 1.1. And here it's 0.12. How do I know that? Well, the halfway point here is 0.1, and it's 1 small square. So that's 0.1 plus 0.02. So you calculate, you show your gradient. when you're doing a gradient calculation, if I see the big triangle drawn on here, even if your results are incorrectly measured from the gradient, it doesn't matter. If I see a big triangle, you get a mark for a big triangle. You should never try and draw a tiny little one because you're not going to get a very precise value. You should always try and draw as big a triangle as you can conveniently get. So calculating the gradient, remember it's a set piece of working. Some of you are getting used to doing this now. It's the idea that it's delta y over delta x, which is y1 minus y2 over x1 minus x2. You're showing the examiner that you know what y1, y2, and x1 and x2 are by actually putting it on the graph there. So just substitute in the values. So it's 3.6 minus 0.4 over 1.1 minus 0.12. And what you end up with is a value, oh well, I made it 3.27 meters. Okay. Now, again, when I'm marking 4. 1 mark, big triangle. 2nd mark, correctly read off the graph. 3rd mark, correct method for measuring the gradient. And the way I look for that is the gradient similar to the one I got in my answers. So when I look at a mark scheme for these particular types of papers, I tend to sort of have a 10% tolerance either way. If it's way out, then I start investigating the graph. For example, if you incorrectly drew your line of best fit and made it too steep, then obviously this would be unacceptably high. But if you use the correct method, you still get the mark, because the only reason why you got it wrong would be because you did your line of best fit incorrectly. So it's quite important to make sure that you are showing working. I can't give you ECF marks unless you take. I'll try again. I can't give you ECF marks unless I can see that that's the only reason why you got the answer wrong. It then says it's suggested the formula below. I'm just going to zoom in a tiny bit here. The formula below, shown below, gives the relationship between the range and the launch angle, where g is the acceleration due to gravity, v is the speed of the jump, is the speed of the jumper as they jump. Okay, so it says discuss whether the results of the experiment prove or undermine the theory. So what we're looking for here is the fact that h, that height, is on the y-axis and sine squared is on the x-axis. Now, if we think about it, their sort of speed at which they jump is going to be constant, and so is g. So this bit here is a constant. So if we use y equals mx, what we have there is a straight line graph through the origin. So we could say that if v and g are constant, the graph is a straight line through the origin. Okay, which, if you look at the graph, it is. It's a straight line through. It's a straight line through 0, 0. Okay, so I'm going to just qualify that and say which it is. Okay, so that is basically what they wanted. They wanted to know that what the question was asking was do those results actually support that formula, support the idea that h is proportional to sine squared theta. It's not asking does it support that those values are exactly correct. How do we know that? Well, the reason why we know that is because we're not given v squared yet. We could find g. If you were given v, that would be absolutely fine, but here we're not given that, because that comes to the next bit. It says use your measurement of the gradient to show that the launch speed of the jumper was approximately 8 meters per second. So if we've got y equals mx plus c, then we know the gradient, because h was on the y-axis and sine squared theta was on the x-axis, we know the gradient should be this m bit here. So the gradient would be v squared over 2g. And on the formula sheet at the beginning, we're told that g is 9.81 meters per second squared. So what we're doing is we're just really using that value to see if we get a value for v out. So v squared is going to be, well, it's going to be 2g multiplied by the gradient. So v is going to be the square root of v squared. So it's the square root of 2g times gradient. So it's the square root of 2 times 9.81 multiplied by the gradient, which came out from me to be 3.27. Common mistake made by candidates is they forget to square root. So we substituted, we then do the calculation manually with your calculator. It comes out to be 8.01 meters per second, which is approximately equal to 8 meters per second shown. Okay, so again, we've gone to an extra couple of significant figures purely so that we can show that it is the same. Sometimes it's going to be a tiny bit different, so we just want to show that you've done the calculation. The mistake that people make, I think, with this is sometimes they just plug, they go to that stage, they don't bother doing the calculation, without realizing that they've got something wrong, and so it's not equal to it, and they lose a mark. It's 1 mark for recognizing that that value is your gradient, 1 mark for substitution, 1 mark for 1 mark for rearrangement, 1 mark for substitution. That's the stage you need to get to actually get the marks. Okay, so that was the 15 marker. The graph question is always worth doing because it's some very, very easy marks. Most of us can draw graphs successfully. All of us can do basic calculations and write the answers on our table successfully. And that's almost half of the marks of the question. So it's always well worth doing. Right, on to questions 5 and 6 were very short. So question 5, you know that you then get something, have something on moments and something on the coplanar forces. Here it's split into 2 questions. You've got 2 small boats can be used to pull a much larger tanker. This is shown in figure 3. The tanker needs to reach a landing stage across the river. Well, that's irrelevant. Calculate the northerly component of the force exerted by boat A. So you want the northerly component. So we've got the north there. So boat A, we've got a force in this direction. So the northerly component is in this direction, which is actually, if you draw a right angle triangle, it's that one. Okay, so if we know this angle's 30, then this angle here will also be 30 degrees. So if that's the case, the northerly component is going to be, well, it's the opposite. You've got the hypotenuse, it's 10,000. And you've got the opposite angle, so the opposite vertex, the opposite side, and an angle of 30 degrees. So we know that the sine of theta, basic trigonometry, is the opposite over the hypotenuse. So that's going to be force over 10,000. So the force is 10,000 times the sine of 30 degrees, which if you plug that into your calculator, remember, particularly if you've just done a maths exam, remember to make sure you're on degrees mode when you do your calculation, but it comes out to be 5,000 newtons. There's your answer. 2 very easy marks. 1 mark for recognizing this bit, 1 mark for the answer. It then says calculate the northerly component exerted by force B. So the northerly component, if we think about it, it's exactly the same question, but we know it's in the opposite direction. Okay, so that again is a 45-degree angle. So we know the northerly component is going to be, and the reason why it's only 1 mark is because using the same technique as before. F over 7,000. So the force is 7,000 times the sine of 45 degrees, which comes out to be 4,950 newtons. Well, I'm sure you recognize straight away that's as near as makes no difference, 5,000 newtons. Technically, I should say minus, but I didn't penalize if people didn't put the minus sign in. But you should recognize that they're pretty much equal and opposite. It then says, hence show the direction of the resultant force acting on the ship by drawing an arrow. Now here's where a little bit of precision is required. If these two forces are pretty much equal and opposite, then the main force is going to be pretty much in the direction. And I'm not going to draw it to scale, just going to draw an arrow. All I was looking for was one mark, just wanted an arrow, and that's the one there. So I'm actually going to make it really clear that that's A part 3. Okay, so that's my answer there to A part 3. What I wanted was an arrow pointing to the right. So then it says calculate the resultant force on the tanker. So what we're doing now is we know that that force is going to be the horizontal or the east component of that force. So it's going to be that component, and the east component of that force, so it's going to be that component. So what we're doing is now we've got the hypotenuse. We're calculating using the adjacent. So we know the force from boat A is going to be the force actually pulling on the boat's pulling with, multiplied by the cosine of 30 degrees, and it's going to be reinforced by the horizontal component of the force from boat B. So that's going to be 7,000 multiplied by the cosine of 45 degrees, which comes out to be 13,610 newtons. Well, for completeness sake, I want to have a suitable number of significant figures. So I'm just going to go for 3 significant figures. 13,600 newtons. Okay, so that was really a coplanar forces question. Yeah, that's part of the vectors topic. The next question is a very easy moments question. This is very, very easy. So the first one is to state the principle of moments. It's a 1-mark question. So if it's a 1-mark question, we just want the simple version. So the principle of moments states that for equilibrium, the total clockwise moment must equal the total anti-clockwise moment, or the moments must all equal 0. About the pivot. Okay. Right. Now it says draw the center of mass symbol, which is a circle with a cross in it, where the center of mass of the horizontal beam is. So it tells you in the question, you've got to be careful. You've got a weight of 40 newtons, and it tells you it's a uniform horizontal beam and a pivot. Universal horizontal beam means it'll be about halfway. For 1 mark, you don't have to measure it, but it should be visibly in the middle. Okay, this is slightly off to the right, but that's absolutely fine. If it's roughly in the middle, that's absolutely fine. To get the next part, you're told the weight of the horizontal beam is 20 newtons. You need to calculate the force F needed to keep the lever in equilibrium. So we're trying to find that force. So here's where a lot of annotation is important. We're told the weight of this mass, the weight, is 14 newtons. It tells you here, okay? So it's a weight, so it's a force, so we don't have to convert it into force. Okay, remember if it's a mass in kilograms, then you have to multiply it by 9.81 to get the weight. And it's worth just annotating that diagram. So there's your pivot point there. We know that's 25 centimeters. What we don't know is that distance, but we do in a way, because it's 25 centimeters plus 75 centimeters. So that's 1 meter. We know that this will be halfway along. This will be the distance from here to here, or the distance from here to here is 0.5 meters. So what we want really is to work out that distance, because we need the perpendicular distance to the pivot. Well, that's going to be 25 centimeters. Okay, or 0.25 meters. You can do either. I'll show you in a second. So once we've got that, we can then sort of apply the principle of moments. So if we apply the principle of moments, we remember that the clockwise moment equals the anti-clockwise moment. So we look for what's trying to turn this clockwise. Well, the two things trying to turn this clockwise are the weight of the ruler, the weight of the horizontal beam, and this force. So I can say the clockwise moment is going to be 25 centimeters. They don't have to convert to meters if you don't want to, because everything here is in centimeters. So as long as the distances are all in the same unit, it'll sort of cancel, any conversion factors cancel out. But I'm going to convert into meters just because I'd like to do that. 25 multiplied by the weight of the horizontal beam, which is 20 newtons, plus the clockwise moment from this force, F, which we don't know, and we know that's 75 centimeters. So that's going to be 0.75 meters multiplied by F equals the anti-clockwise moment. So the only thing trying to turn this whole thing anti-clockwise is this weight here, 40 newtons, 25 centimeters away from the pivot. So that's 40 newtons multiplied by 0.25. So the force F, to rearrange it, is going to be...
Gary, how do you know the weight is 20?
How do I know the weight's 20? It tells you here.
All right.
Okay. That's why you notice that when I'm going through this, I'm circling things like nobody's business. The reason why you do that in an exam is you're trying to pick out all the useful information that's there. It's a key skill of an engineer, I think, is being able to read a document and get the right information out of it. So it's 40 times 0.25. Thank you for asking that question. 0.25. Now I'm going to subtract this one over here. 0.25 times 20. Then divide both sides by 0.75. It's just a rearrangement. Always well worth writing it out first, because remember, if you're typing it into a calculator, it's a keyboard, you make typos. So if you've got it written down, it makes it a lot easier for you to do. And that comes out to be 6.7 newtons or thereabouts. Easy as that. Okay, so what we're looking for there is 1 mark for using the principle of moments, 1 mark for correctly finding the clockwise and anti-clockwise moment, 1 mark for the answer. I gave the benefit of the doubt on some of the working. As long as I could see some correct working, I assumed that you were using the correct method, particularly if you got the right answer. Are you all okay with that? Everyone okay?
Gary?
Yep.
Could you please quickly go over question 5 again?
Yeah, sure. So if we look at question 5, you've got 2 small boats used to pull a much larger boat. So it's shown in figure 3. So you've got 2 forces. You've got a 10,000 Newton force in that direction, and you've got a 7,000 Newton force in that direction. And you're given the angles for those forces. So you want to work out the northerly component. Remember, every force at any angle it's comprised of two right angle forces. They're called the components. So the force you wanted was that one, and we know that that's 30 degrees. So we want to find that force. Does that make sense?
Yes.
So you're literally doing a right angle triangle question. Same goes with this one. It's almost exactly the same question. Here we've got a force here, and we know it's 45 degrees. It's got a horizontal component or an easterly component, and it's got a southerly component there. So it's a right angle. We know that that's 45. So again, we're trying to find that opposite force. So it's the sine of the angle. Okay.
But Gary, isn't that the southern force? Or
Well, it is. So that's why it's negative. But in
oh,
this case, actually, I was only really after the magnitude. It's only worth 1 mark. So I was only after the magnitude. So if you wrote 5,000 or 4,950, I gave the mark anyway. But technically, it should be negative. You're quite right. It's negative because it's a northerly force and it's obviously in the opposite direction.
all right.
Okay. And then when you add the two forces together, of course, you end up with something as near to zero as makes no difference. So if the last part is just basically we've got the two forces, we've got this force, this component, plus this component. Okay, so it's the hypotenuse multiplied by the cosine of the angle instead of the sine. Then you add them together because they're both pulling. Okay.
Sorry, could you go over IV again? I don't get what you said.
Right. So we've got the force from the first tug here. Okay, so this is the horizontal force, because if we look at it from the previous question, we know that then the resultant force is going to be in that direction, or more or less. It might be slightly up a tiny bit, but we're going to ignore that. So if you recognize that that's then a horizontal force, we've got the horizontal component from the force from this boat, plus the horizontal force from the component of this boat. They're both going to pull together, aren't they?
Yeah.
So if they're both going to pull together, then the two forces will actually add together. So the force from this boat is this side of the triangle. So it's the adjacent side. And you've got, you know, the hypotenuse, which is 10,000. So it's 10,000 multiplied by the cosine, or sorry, 10 multiplied by the cosine of the angle, plus 7,000 multiplied by the cosine of that angle, 45 degrees, because we're looking at the horizontal now. Yeah?
All right.
Okay. So we're just adding them together.
Thank you.
Okay. Right, and then we come on to the multiple choice questions. So it then says select one answer for each question by each question only by circling the correct letter. So we're looking for one, it's multiple choice, there's only one right answer each time. So which of the following contain both vector and scalar quantities? So we want things that we want to have a question here where there's both a mixture of things with and without direction. So mass, speed, and distance, they're all scalars. They don't have direction. Here, force is a vector, velocity is a vector, but time is a scalar. So it's probably B. Now, whenever you get something like that, I always advise checking the rest of it. So velocity, remember, is speed in a given direction. So that's a velocity, that's a vector. Acceleration is a vector, and so is weight, because it's always pointing downwards. Here, mass is a scalar, luminosity is a scalar, and speed is a scalar, so it's definitely B. It's got a combination of both of them. Right, now, this is all about estimation. The most likely value for the mass of an adult person. Not an easy one to work out, but if we think about it, we can sort of figure this one out without too much difficulty. If we think about it, 20 kilograms, well, that's about the weight of that's about the mass of your suitcase when you go on a flight. So that's clearly too light. 600 grams, well, 1,000 kilograms is a ton. So here we've got somebody who weighs more than half a ton. Well, not an average person. Okay, there might be some who maybe weigh that much, but not many. Even 200 kilograms, I think, is a bit too much. So the correct answer here is D. It's about 60 kilograms. Remember, it says an adult person, so it could be a man or a woman. It could be somebody who is quite young. It could be somebody who's quite old. So we're looking at anything between sort of 50 and 100 kilograms. Anything about 100 is sort of going outside the averages. But 60 kilograms was about the right answer. Right, number 9, I want to dwell on number 9 because many people got this one wrong. It says it wants the base SI unit. Remember, the base SI units are length, which is in meters, time in seconds, current, which is in amps. They're the base quantities. There's moles, candela, and so on. Okay, they're the base units. Remember that things like watts and joules, they're derived units. So a lot of people said A was the correct answer because they just thought it was the SI unit of power. The base SI unit is to do with these basic quantities. And the way you do this is you say that power, well, you can do a couple of different ways of doing it. So power, we know, is force times velocity. That's actually featured in question 2. So if that's the case, we know force is mass times acceleration multiplied by the velocity. So the mass is in kilograms, acceleration is in meters per second squared, velocity is in meters per second. So we end up with kilograms. We've got meters here multiplied by meters here, so that's meters squared. Seconds to the -1, seconds to the -2, add the two together, we end up with seconds to the -3. Okay, so it's got to be B. Number 10, this is a bit of a trick question, this one. The toy car travels horizontally, experiencing a horizontal force of 15 newtons and a mass of 4 kilograms. What is the approximate value for the net force on the car, ignoring air resistance and friction? Well, there are no other forces, so it's 15 newtons. You could try and add the weight of the car, I suppose, if you're pedantic, but it wouldn't be similar to any of those, so we're not going to do that. So it's a bit of a trick question, that one. Which of the following is a possible definition of impulse? Remember, impulse by definition is the change in momentum of an object. All the others here actually don't make any sense. Force per second, well, that's not anything. Changing kinetic energy, well, that's not impulse, is it? Because impulse is to do with change in momentum. Acceleration per unit mass, again, that's not really anything. So it's not really, these two aren't really anything at all. So it could have been this one, but it isn't, because we know that impulse is the change in momentum. Right. Which of the following is a description of an elastic collision? So an elastic collision is where kinetic energy is the same before and afterwards. So here we've got two cars crashing head on, sticking together. Well, if they crash head on, then we're going to lose kinetic energy if they stick together, if we think about it. Because if whichever way you try and do it, if you've got a car and a car there, we know that what we end up with, if they've got equal and opposite momentum, then if they stick together, then they'll have no velocity afterwards. So here, quite possibly, we're going to be losing kinetic energy. How else do you know that? Well, if you see a car crash, you see the bonnets get dented, the car gets deformed. So there's got to be some work done in changing the shape of the car. So obviously, kinetic energy is not conserved. In an explosion, you start off with zero kinetic energy, and then all the particles have kinetic energy afterwards. So it's not conserved because you're actually adding energy. So you've got two protons almost colliding, but being repelled and moving away from each other. So they sort of come together, two protons, they come together and then they move apart. Well, there's no change in anything else. So that could be the answer. But we'll just have a quick look, moving on here. A book stationary on a shelf. Well, that's not really a collision, is it? I mean, that's just equilibrium. So it's not that one. So it's got to be C. So even if you're not certain about this answer, although it was one of the examples we talked about when we talked about momentum when I was teaching it, actually, it's the only one that could possibly be the right answer. Okay.
Sorry.
Yep.
Well, since they don't collide, is it still considered a collision?
Yeah, because what they're actually doing, a collision is where two forces interact. So here they don't actually collide, but they will actually in some way bump into each other, but they just won't actually touch. And in fact, that's actually what happens in the real world. You get two positively charged particles. If they're subatomic particles, they'll tend to collide but not actually touch. They'll push each other away again. So it is a collision. It's just instead of being a physical sort of touch, like say if you can imagine if you've got springs on either side of them, okay, the springs are actually not mechanical springs; they're just the force of electrostatic repulsion. So it is still technically a collision. Does that make sense? Okay, good question. Thank you. Right. Any questions about the paper first of all? No. Well, those of you who did it, obviously, I've fed back your grade, and I've also attached on Show My Homework your actual marked paper, so you can see how well you did on which question. I'm going to probably talk for about another half an hour at the most, I think, and then I'm going to give you half an hour to really sort of go back over your paper and just see where you went right and where you went wrong. So I'm going to talk a little bit about a couple of topics where I was seeing some minor errors. There's nothing big, nothing major, just a few things to clear up. The first one is about coplanar forces. If you have any force, any vector quantity, I tend to use forces when I'm using examples because that's the easiest one to use. The forces can act with any vector quantity has a horizontal component and a vertical component. Okay, if we think about it, we're pushing a certain amount of force in that direction, a certain amount of force in that direction. Okay, we combine the two forces and this is kind of your resultant. So in some questions, you're given the resultant and you've got to work out the two components of the force. Now, the reason why that is because obviously sometimes you might be doing work against gravity. So you have to think about the coplanar forces. And I'm going to talk to you a little bit about that because I think this is one that people found the most difficult. It's the idea that basically you're just solving a triangle question. So FV here is going to be F sine theta, and FH is F cos theta. Okay, it actually works out. What I see from that is that you just need to use your sort of your basic, or almost, well, pretty much GCSE maths to actually work out the two components. Where that comes in handy is if we've got a cannonball firing a cannon, sorry, a cannon firing a cannonball with a certain velocity. That velocity has two components. There's a horizontal component and a vertical component, which we call VV and VH for sake of argument. Okay. Now, if we think about it, if you've got a cannonball being fired at a particular angle and a particular velocity, you know that if we ignore air resistance, that horizontal velocity is a constant. So in terms of the horizontal velocity, we're using the constant velocity sort of physics, but VV is going to be U plus G UV plus GT. Okay. It's a constant acceleration. So what we have to do is be very, very careful about how we go about doing this particular type of physics. The reason why we choose right angle components is actually forces. Any vector at right angles has no effect on the vectors. So, for example, it doesn't matter what your horizontal component of your velocity is; it has no effect on the vertical component at all, except where it's part of the resolution of the sort of resultant vector. So even if we kept this vertical component of velocity constant, we know that it would actually it would spend the same length of time in the air, even if this value was much higher, which is why you can't just take off by running very fast. I don't know about you, but when I was a little kid, I used to sort of run off tables to see if I could fly. Obviously, that was when I was very, very young, and I worked out very, very quickly at the age of about 10 that that really didn't work. But that is the basic physics behind projectile motion. Because when we think about it, if you've got a projectile follows that parabolic path, the speed at any particular vertical component is the original vertical component plus GT. So, for example, if we wanted to work out the time spent in the air, well, the initial vertical component is going to be UT. As it goes down, we know that would be minus UT. Okay, so try again. UV, not UT, be minus UV. Okay. So we could actually work out the length of time that the projectile spends in the air. So you can say, okay, well, if that's the case, well, it's going to be T is going to be equal to, well, it's V minus U. So that's going to be minus UV, which is the final velocity, final vertical velocity, because it's going downwards, minus UV. Okay. And then we divide all that by G, 9.8, when it's negative 9.81, we end up with...
Or isn't it meant to be minus VV?
It's UV, because VV is what the vertical component of the velocity is at the end, and it's going to be equal to minus UV. That makes sense? Because really we're using V minus U over acceleration, aren't we? Now, if we think about it, it's 2 minus UV over G, where G, well, here we defined up as being positive. The acceleration due to gravity is downwards, so it's minus 9.81. So actually, we can actually just say it's 2 UV over G, couldn't we? Yeah, over 9.81. We can ignore the minus sign. Does that make sense? So you can work out the time. Well, you know the time. That is basically going to be UV. I should say it's, dear, oh dear. We know that UV is going to be the sine V times sine theta. So it's 2V times sine theta over G. You can work it out. And this is about as hard as it'll ever get. It's certainly at foundation level. So you can work out the time in this particular example. And then you can work out the range, because the horizontal range is the horizontal velocity, which stays the same, multiplied by the time. So the horizontal range is equal to 2 times the speed of the cannonball out of the cannon, multiplied by sine theta, times T, sorry, yeah, no, sorry, try and get that right, over G, I do apologize, over G, multiplied by VH. VH here is is V times the cosine of theta. So that would be 2 times, you've got V there, V squared, sine theta cos theta over g. Whoops, off the bottom there. So you can use that resolution of vectors to do some pretty complex physics. Now, this is not something you're asked to be able to derive. However, it helps if you recognize it. And in fact, in some of the graph questions, you know that the graphing question in the Unit 2 exam tends to be, it's not always, but it tends to be about projectiles. So you need to be sort of familiar with that. It might be, say, to do with the range, how far the cannonball would go with respect to its launch speed, or it could be the range with respect to the angle. So you just need to be aware that that's where it comes from. But it's all to do with resolution of vectors. And it's the idea that you can split any vector into horizontal and vertical components. Does that make sense? Okay, I'll either assume that that makes sense to all of you, or that some of you might have flipped your phone over and gone back to sleep. I don't know, but hopefully you've picked up on that. I'm certainly getting a lot of questions, which is a very good thing. The other thing I wanted to really sort of dwell on a little bit was on momentum. I think some people are still getting a little bit confused with the concepts actually sort of used in momentum. There are two basic aspects to the momentum sort of topic. There are the collisions or interactions or explosions, and then there's impulse questions. Remember, impulse is all about changing momentum. So when you get a collision, if you've got two masses colliding, let's say they collide and they stick together. You know, the total momentum before and after is always going to be constant because there are no external forces. And that's the bit that people miss when they talk about principle of conservation of momentum, is the idea about no external forces. So collisions are all about not having an external force. Now, if you've got a collision, you've got the momentum before. Now, as V1 and V2 are in the same direction, we add them together. If V2 was heading if V2 was heading in the opposite direction, that would be negative, is equal to the total momentum afterwards. So the total momentum, if they stick together, then they're going to have a combined mass. Okay, and so you can work out the sort of the final velocity afterwards. Common scenarios you'll get, scenario one is usually to do with two cars colliding or something like that, or an experiment with two sort of little trolleys colliding. The other example that's very, very common is a bullet hitting a block of wood and embedding itself on it, which is exactly the same physics. The only difference is that the M1, the mass of the bullet, is tiny and V1 is quite big. Apart from that, it's pretty straightforward. The impulse is an area where people do get very, very confused, and they find it very, very difficult to sort of work out what's going on. Well, the thing with the impulse is it's all about the idea of a change of momentum. That is what an impulse is. Delta always means change. Okay, so we got the idea. You basically use the idea the force is the change in momentum divided by the time taken for that change. Where that comes in handy, well, we talk about car safety, the idea that if you've got a crumple zone on the car, then you increase the time of the collision for the same change of momentum, which decreases the force and therefore decrease the likelihood of you having an accident, of you having any kind of injuries, which is why they have things like airbags on cars, crumple zones, where the bodywork of a car is designed to actually sort of collapse when exposed to a force during a collision. There are lots of other examples. For example, if you're trying to hit a nail with a hammer, when you hit the nail with a hammer, what you do is you give the hammer a large momentum, and it's the change in momentum over a very, very short time that gives a very large force that enables you to hammer a nail into a piece of wood. You also get it in sports. If you're a track runner, you have shoes which are designed to increase the collision time between your foot and the ground, which then increases that time and decreases the force for the same change in momentum, which it decreases the force on your feet and also then subsequently on your knees and other joints in your body, which is why if you're a professional runner, you should use proper running shoes, not try and use a pair of sand shoes or plimsolls. It also comes in handy if you are a footballer. If you're a footballer, you understand that if you give your foot lots of momentum, then you exert a large force on the football. But also, if you're going to slide to a halt, if you increase the time that it takes for you to slide to a halt, you decrease the forces on your body, and therefore your likelihood that you'll be very badly injured during a collision with another player, or if you're slipping over. So it comes in handy with a lot of different things. It also comes in handy with jet forces, because a lot of examples involve a change in momentum due to a change in velocity. But actually, if we think about it, if you've got a jet force, let's say, sake of argument, you've got a hose pipe, okay? And that hose pipe fires water at a particular velocity, at a particular speed. Now, if we think about it, what we do is we think about the cylinder of water being fired out of there in unit time. Obviously, that would then be velocity times time. That's the length of the water, that's the distance the water travels in a given time t, okay? And the nozzle has a cross-sectional area A. So what we end up with is the idea that the volume of the water being fired is the speed of the water multiplied by A multiplied by the time taken. So if you know the volume per second, the volume of water per second, you can work it out from the speed of the water and the area of the nozzle. Why is that important? Well, it comes in very, very handy, because if we think about it, that volume is mass over density. So if we know the mass flow rate, that's going to be the, so it's volume times density, isn't it? So it's going to be the volume flow rate multiplied by the density, which is the speed the water's coming out, multiplied by its cross-sectional area, okay? And that comes in handy because if we take the idea about force being the rate of change of momentum, here the speed is constant, but it's the mass that's flowing out with any given particular sort of space of time. So that's what we call the mass flow rate, the number of kilograms of water coming out of that hose pipe nozzle there per second. So we can actually do some clever physics. Excuse me. So if we know the speed, the mass flow rate is the speed times the area times density, the speed times the area times density. So the force from a nozzle is equal to V squared times the area times by the density of the water. Now, why is that important? Well, if we think about it, if you've got a hose pipe with a very wide area, then obviously for the same mass flow rate, we're going to get a very low velocity. But the force increases with the square of the velocity, but it's only proportional to the area. So if you increase the area, you decrease the velocity, you'll have a decreased force, which is why if you just have a tap running, the water doesn't come out with much force. But if you put your thumb over the end of a hose pipe or the thumb over the end of a tap, it squirts out and seems to be exerting more force. And that's why. Okay, this is actually why. It's also handy to know about jet forces, because we're using water here as an example. Well, a classic story, I'm going to leave you with a little story. My story is about when I was about sort of 14, 15. I worked with a couple of friends of mine. We washed cars to get some pocket money. So we had one of my friends was quite well off, and he had a portable power washer. Now, with the power washer going at full tilt could had a mass flow rate of about 2 kilograms per second. Okay. The area of the nozzle, well, that was about trying to think, that was round about sort of about 2 square centimeters. So that would be 2 times 10 to the minus 4 square meters. Okay. And we worked out the velocity of the water coming out was something in the region of about, well, it was about 20 meters per second. Came out about 20 meters per second. So if we had a force, that would be 20 squared multiplied by 0.0002 multiplied by the density. Now, density of water is about 1,000 kilograms per cubic meter. So it was 20 squared multiplied by 2 times 10 to the negative 4 multiplied by 1,000 is the density of water. And so that gave us about 80 newtons, which was equivalent to lifting about 8 kilograms, which is quite a large force, which came in very handy because back when I was that age, obviously I wasn't particularly well off. I didn't have a lot of money, but I was washing cars in a village where a lot of my schoolmates lived, and their parents had lots of money. So they would sit on the wall and they would make fun out of me for washing cars for money. Now, of course, if I used the power washer, I could exert a force on them of 80 newtons and knock them off the wall, which is what I did and then ran. But you can see that you can apply a jet force. The same thing goes if you've got, say, a helicopter. If you've got a helicopter, there's your helicopter, very badly drawn. If we think about it, there is a cylinder of air below the rotors, which has an area. So it's exactly the same physics. Ooh, hang on. Camera's gone off again. Which is exactly the same physics. The only difference is the density is very, very different. So if I have a velocity of air of, say, for a helicopter, it'd be about 100 meters per second-ish, let's say. It's quite fast, but let's just pretend. So about 100 meters per second, an area of, say, 2 square meters. I could work out the lift force from the helicopter because I could work it out as being 100 squared multiplied by an area of 2 meters. Density of air is around about 4 kilograms per cubic meter. So that's 10,000 times 8. That's going to be 80,000 newtons, which is quite a lot of thrust. So you can work out things like the force from a jet engine, the force from a helicopter, the force of a water jet, using the ideas about impulse. And just going back to that first principle of force is delta mv over t. The difference here is the m is changing, the v is constant, whereas in a lot of cases, when you're looking at stopping forces and accelerating forces, it's v that's changing and it's m that's staying constant, because when v is changing, we know that that would be m times delta v over t, which is the same thing as ma, which is Newton's second law of motion. So those are the two offshoots with momentum. So you can do quite a lot with those two ideas, but what do you need to take away with you? You need to take away the principle of conservation of momentum, the idea that for no external forces, the total momentum before the collision is equal to the total momentum after the collision or interaction or explosion, and the idea that the force exerted is the rate of change of momentum with respect to time, and that the change of momentum is called the impulse. The only other thing to remember there is that if you get a force time graph, for a particular collision or stopping force, if we think about it, if the force is constant, then the change in momentum is equal to the area, which is force times time if the force is constant. If it's not, then it's still the area under the graph. So for example, if we have a constant stopping force at a particular force and time, if we had a stopping force which was more like, more like that, the area here, this area, is almost exactly the same. So it's the same change in momentum, but the force is the maximum force is much higher. So that's just something to remember. So the point being that if you were to halve the force, you'd have to double the time for the same to get the same area and therefore the same change in momentum. Does that make sense? Well, hopefully that does. What I will say is I'm going to give you about another half an hour. What I'd like to do in that half an hour, I think, rather than listening to me talking for, you've listened to me talking at you for, for nearly 2 hours now. Rather than listening to me talk for another half an hour, which I think you're probably a bit fed up with by now, I'd like to go back over that exam paper that you did last week, and just make sure you understand how to answer it. So what I'm going to do is for the first sort of 15 minutes, I'll let you just work independently. And then what I'll do while you're doing that is I will convert this video and put it up on YouTube, and you can use the video to then sort of go back over the paper if there are any bits you couldn't quite remember. Is that okay?
Gary, the previous videos you've uploaded, are they on Show My Homework or on your YouTube?
They're on, well, they're both. What it is, it's on Show My Homework, but what I've done is I've replaced the Zoom link, because obviously it's redundant after the lesson. Replace the Zoom link with a YouTube link. So you click on it, and then you get the video. I strongly recommend watching the videos again, because actually, if you watch the walkthroughs, you get more and more familiar with techniques, and sort of the ways to actually solve a problem, even if the question is something that's a little bit weird or a little bit different to what you're used to. Any other questions? Right, so what we'll do, tomorrow you're getting another paper. I've put that up already. That'll be ready tomorrow morning. I'd like to spend tomorrow's lesson going over the whole paper, spend some time on it, do your level best with it. And what I'd like you to do is with your answers, either on a printout of the paper or on a piece or on some lined paper and graph paper, I'd like to try and answer every question, take a photo of it. But what I'd like you to do is try and put it onto a PDF document. You can actually download PDF scanners from the App Store, from Google Play, which will enable you to take your photos and put them together onto a PDF document. And that's a lot easier for you to send, and it means that you'll get your feedback much more quickly. So with tomorrow's paper, I'd like to do the paper tomorrow in the in the triple lesson that you have. It's an hour and a half's paper, but as I said, I'm trying to give you a bit more time at the moment, because I want you to really sort of practice, and I want you to really attempt the questions. I don't want to see question 4, I couldn't do it, or question 4 just completely left blank. If you leave something blank, all I know is you couldn't do the question, or you didn't want to do the question. I don't know which it is, actually, to be honest, but it could be either. But if you leave it blank, I also don't know how I can take you forwards. If I see a reasonable attempt, I can see where the misconceptions are, and I can clear them up in these walkthroughs. And this was actually quite a specific walkthrough. You noticed I went through some questions in a lot more detail than others. And that's because most of you got certain questions right, but there are certain questions where I could see that I need to actually sort of help you. And also where I was marking, I could actually identify things like coplanar forces, momentum, 2 areas where quite a few people are still finding it quite difficult, and trying to help you with that. So that's what I'd like you to do in this lesson, for the rest of this lesson. The first bit is really just sort of make sure you downloaded my feedback from the paper from last week, and just really gone through it to see where you did and didn't get marks. in a couple of cases, I got blurred. I was sent some blurred pages. Just remember for next time, just make sure it's in focus. Don't bother sort of redoing it now, because obviously you've had the feedback now. But just remember for the future, just make sure if you take a picture of your work, make sure it's in focus, please. Apart from that, I will see you. Well, I mean, I'll be around on. I'm still here in tomorrow's lesson. So if there is anything, just ping me an email, and I will. I'll try and answer your questions as best I possibly can. If not, I'll feed back that paper on Thursday's lesson. You'll get some more feedback. But what I'm seeing generally is a lot of good progress. So well done, everyone. All right, take care.